Hello. Obrigado. So good morning, everyone. I would like to start thanking the organizers for this invitation, and also thanking all the IIP staff for welcoming me here very warmly. I am Marcelo Barbosa da Silva Neto. I am the guy between you and lunch, so I hope I make this pleasant for you. And I'm going to present a work that I've done in collaboration with Felipe Pinheiro from the Physics Institute in the Federal University in Rio de Janeiro, where we have a proposal for controlling spontaneous emission through strong correlations. And this would allow us to have photons on demand if we have an emitter in transparent metals. So there's a lot of things here that I have to define and discuss: emitters, spontaneous emission, and the possibility of having transparent metals. And I organized the talk like this. So I'm going to talk about the aim or the will to make single photon sources, the physics of spontaneous emission, and then the Purcell effect. For those who don't know what the Purcell effect is, I'm going to define it, but it's a way of enhancing the spontaneous emission, because this would be nice if you want to build a single photon device. Then I will discuss what happens if you place quantum emitters embedded in metals. Normally, we would not expect to see anything very exciting, but if these metals are correlated, there are strong correlations, and they don't even need to be so strong, then you can make them transparent conductors, and things begin to get interesting. So I will calculate the spontaneous emission rate for quantum emitters that have been embedded in these strongly correlated transparent metals, and show you how we can have photons on demand in these systems. And then I leave you with the conclusions. So today there is a lot of search for single photon quantum sources using quantum emitters. And what is a quantum emitter? You can have, for example, a single atom in a cavity, and if you prepare the atom in an excited state, when it decays, it can emit a photon, and this is considered a single photon emitter, single photon source. You can have semiconductor nanocrystals, and you can see that if you vary their size, you can have different emission energies or emission wavelengths, and you can fine-tune this with the size to get all the colors of the spectrum. You can use quantum dots. Here's an example of a zinc blende grown on a surface of cadmium, and this pyramid here acts like a quantum dot. You can also, because it's a finite structure, finite size structure, the band structure become discretized, and you can have transitions with emission, absorption, and all this physics that we know. There's also, for example, the nitrogen vacancy defect center in diamond. And when you have here a vacancy in the nitrogen atom, this has a electric dipole moment, and it can, transitions of this electric dipole moment can also emit light. This is actually, this is a diamond, so this is done in diamond. And Leonardo Menezes from the Federal University of Pernambuco, he has one of these crystals with one of these defects, and he's doing experiments with emitters in liquid crystals, and this is something that we have been collaborating as well. And you can also have a semiconductor nanowire. This is the cover of Nature Photonics. This is a nanowire, and you can see that depending on the length and the radius of the nanowire, you can also control spontaneous emission. So I showed you a few sources, photon sources. So now let me now review the physics of spontaneous emission, because I will use this later on. So the basic physics is all of those sources that I've showed you, we can model as a two-level system. And the idea is you prepare the atom in an excited state. When it goes to the lower energy state, it emits a photon. And I'm going to be speaking about spontaneous emission, not light amplified spontaneous emission of radiation, where to have a laser you have to shine light and then you get the amplification. So this is, you prepare it on the excited state, emits a photon. And that is, as I said, you can do this with atoms, molecules, quantum dots, nitrogen vacancy defects, and many other sources. The most simple Hamiltonian that we can use to study this problem is the so-called Wigner-Weisskopf Hamiltonian. You have here the two-level system with splitting of the energies h bar omega naught. You have here the photon modes labeled by wave vector and polarization. And you have coupling. This is a dipole coupling. And you have here either transmission, emission, or absorption of a photon. So the two-level system is a discretized part of the Hamiltonian. And you see here that this dispersion of the photons, they are, as we know, they are linear dispersions. The slope here is the velocity of light. And this is typically the coupling constant. You have polarization vectors of the light coupled to the expectation value of your dipole moment. Yes? Yes, then you quantize the electromagnetic field and you get this Hamiltonian if you have an atom coupled to the light. Yes. So, I've been speaking about spontaneous emission. Spontaneous emission, there is a rate we can calculate, that's spontaneous emission rate. And how do we calculate this? As I said, we prepare we prepare the system in the excited state, so this is the initial wave function. You have the electron on the excited state and 0 photons. At a later time, the wave function can be written as a combination with a certain probability of being still on the excited state, and the sum over the probabilities of being in the ground state. And if you use Schrödinger's equation for the Wigner-Weisskopf Hamiltonian, you get this a nice linear differential equation here, where this is the spontaneous emission rate, this gamma naught in the vacuum, and this is the lamp shift. I'm not going to be speaking about the lamp shift, so I'm going to forget about this term right now. And its solution is, as we expected, exponentially decaying, and the rate of decay is this quantity here. And this is what we call the spontaneous emission rate in vacuum. And it's nice to emphasize it's quadratic in the dipole moment, cubic in the frequency, and has all these other constants here. Well, we can rearrange this expression. We can put in evidence 2 pi over h bar, something here in parentheses. And if we remember that the electromagnetic density of states in vacuum goes quadratically with the frequency, so this is Institute, Daniela Zillard, o Winter, Felipe Rosa e Carlos Farina, and they were placing the emitter close to a surface of a material that's undergoing percolation transition. And you can see here, they calculate for the perpendicular polarization of the electromagnetic field. They have an enhancement exactly at the percolation threshold. They have an enhancement of the spontaneous emission rate with respect to its vacuum value. So this is a nice result showing that indeed you can have not only be close to some non-trivial boundary condition, but it shows that a phase transition can cause enhancement of the spontaneous emission rate. That example, the emitter was outside the material going through the phase transition. This is an example of the emitter inside, embedded in a two-dimensional photonic lattice. The red dots here, the sites are occupied. The sites are emptied. So by going through also again a phase transition, you can see here that the spontaneous emission rate develops a component at high. Well, the spontaneous emission rate here is enhanced, and this is the Purcell effect. Well, we are not going to discuss boundary conditions or to place the emitter inside a photonic lattice. We are going to consider the problem of spontaneous emission in dielectric and conducting media. So if you have here a nanoparticle that can represent any of these two level systems that I've been discussing. So you can have the high energy, the excited state where it's hot, so it's represented by the red. And when it goes to the ground state, it can emit a phonon. If it's inside a material, it can even excite a non-radiative process, for example, creating a particle hole. And what is more fashion nowadays is the connection with the surface plasmon physics. So we are going to be discussing the radiative decay when this nanoparticle is placed inside some media. Remember that, well, I forgot here H bar, but remember that for the visible, H bar omega 0 has to be inside this window here. So what's the problem of, for example, having emitters inside metals? As we know well from electrodynamics, the electromagnetic dispersion gets modified because now I have a relative refraction, relative dielectric constant here, multiplying the vacuum value. And if we solve this, well, recalling that the relative refraction index here is 1 minus omega p squared divided by this denominator, where this omega p is the plasmon frequency. If we plug this in this the equation above, we get this dispersion relation. So it's no longer linear, straight line, as in the vacuum case. And we are going to consider, for simplicity, the case without losses. So we're going to consider gamma equals 0. If you plot this, or what would be the vacuum result becomes now this dispersion here. And if you divide the frequency by the plasma frequency, you have here 1. So this is the plot that I've made. So what does it mean? What does it mean? If I start, again, with the Wigner-Weisskopf Hamiltonian, in the coupling constant, I have also to replace what I had here epsilon 0. I have to put also the relative contribution. And recalling that the calculation, it's 2 pi over h bar, something square, density of states, I want to use Fermi's golden rule. And in order to do that, I have to decide to define my initial and final states. So for the non-interacting Hamiltonian, I can split these two states into excited states and 0 phonons. This is my initial state. Ground state, 1 phonon. This is my final state. And I can calculate the transition amplitude. We do this with the Wigner-Weisskopf Hamiltonian, we make use of the algebra associated to creation and annihilation operators, and we end up with this result. It's very convenient, 2 pi over h bar, a matrix element square, and a delta function here. But in order to get the transition rate, I have to sum over all final states labeled by k and lambda. The matrix element square just gives me the projection of the dipole moment in the direction of the polarization of light. For an isotropic system, this is simply mu squared divided by 3. So if I do the summation, this is the last line is the interesting one. Again, I obtain something which is 2 pi divided by h bar, something squared, and this is simply the definition of the electromagnetic density of states in the medium. So with this definition, and I just defined this coupling constant g square, we conclude that simply by placing the emitter in a metal, I go from the vacuum result to this other result here. 2 pi over h bar is the same, g square is the same, but I get two things here. I get 1 over the real part of the dielectric function, and the density of states doesn't carry this 0 anymore. It's the density of states inside the medium. So, one final slide of calculations. For this dispersion relation, and knowing that the index of refraction is the square root of the real part of the dielectric function, we can calculate the density of states to obtain this result here. Is the real part to the 3/2 power. Now we plug this back to the calculation of gamma, and there's a nice result, which is simply the spontaneous emission rate inside the material, the metal, is just the result of the vacuum multiplied by the electric constant, the index of refraction. So what does it mean? We all know this figure here. This is plotted the real part of the dielectric function as a function of relative energy divided by the plasmon frequency. This part in white, I can have transmission, and this part shaded, I have total reflection. So there is a problem. I cannot have spontaneous emission if I am inside a metal. No news, because the metals, they don't allow propagation of light. So this means that here is my dispersion relation inside the material. If the two-level system has energy smaller than the plasmon frequency, I cannot emit. But if, for example, the two-level system has the energy splitting is larger than the plasmon frequency, then I can emit. So the whole thing is how omega 0 is related to the plasmon frequency. So let's talk about the materials now. What kind of materials can we use to try and make transparent, good conductors? Because the main goal here is to find transparent, good conductors, because this is what they are interested in: photovoltaics, solid-state lighting, making displays. So they want something that it's a good conductor and transparent. So far, people have been trying with semiconductors, because semiconductors are wide band gap materials. They have good coefficient of transmittance, but they are not very good conductors. The highest number of carrier concentrations obtained so far in a semiconductor is 10 to the 21, while the simplest metals, even the porous metals, they already have 10 to 22, 10 to 23 electrons. So it's hard. They really have to look for heavily doped semiconductors. But as you can see, the plasmon frequency is very small. It's where this part of the dielectric function cuts 0, so it's really low. It's much smaller than half electron volt. So visible is around here. So they are really transparent. I will get not there, but close. I will drive by, and then we can talk. So the problem with metals is the solid line here is the expression that we obtain for the free electron gas, for the dielectric constant of a free electron gas. And you see that for gold, for example, it follows very nicely. But here we have the so-called interband transitions. And they get things complicated because they don't allow the dots to cross. And then you would go to the good region of transparency. But they keep the dots here way below until 6 electron volts, which is way higher than the visible. And then you cannot make it transparent. So how to make a metal transparent? That's the thing we are trying to this is already done. I'm going to present you the path towards making a metal transparent. And this is strong correlations. So as I said, people normally try to go up this hill here. Why? Because the main object here is the plasmon frequency. We cannot change E squared, we cannot change the epsilon 0, but we can change N or M star. So if you have a light mass semiconductor, like for example ITO has a very small effective mass, so it has a rather large plasmon frequency. But if you can start increasing the carrier concentration, you are going in this direction. What's plotted here is the plasmon frequency, and here is the conductivity. So you want good conductors. That's why you are heavily doping semiconductors. You are trying to increase N. That's why it's in green here. So we are going up, but you cannot go too much to the right, because otherwise the plasmon frequency will enter the visible and you don't get what you want. So these guys here, they published a paper in 2015 where they tried the other approach. Let's start with metal. And from metals, let's start adding strong correlations, because in this way you increase the effective, I want transparency in the visible. I want to make a device that I see something blinking. So I want to be in the visible. So here, I'm sorry, this should be increasing the effective mass, because if you increase the effective mass, the plasmon frequency decreases, and then you go, here is right, increase effective mass. Then you go in this direction. So the two candidates, the most prominent candidates are strontium vanadate and calcium vanadate. They have plasmon frequencies as small as 1.33 electron volts. They are to the left of the edge of the visible, and they have conductivity much higher than the best semiconductor made. So these are two nice candidates to make photovoltaic devices, and everything is summarized in this diagram. Here you have the conductivity. Here you have the ratio of the renormalized effective mass to the bare effective mass. And this is the effective mass renormalization factor. If it's 1, you are here in the simple metals where there is no correlations whatsoever. If you start introducing correlations, Z starts to go to the left, increasing the effective mass. And here is strontium vanadate. It has there is a lot of large mass renormalization, but still we are in the metallic. It's a correlated metal, and only crossing this line you get to the Mott insulator. So, yeah. So it's not a problem of the free electron gas, and it's not a problem of the Mott insulator. It's intermediate strength of the correlations. But still, here you can see that the real part of the dielectric function has a nice Drude-like behavior, as well as the imaginary part is very small. It can be considered 0. And here, for the two materials, the calcium vanadate and the strontium vanadate, you see that they have a very high transmission coefficient of the order of 80%, depending on the width of the film. So they are really, they transmit light very well, and they would be very well suited to making devices. And not only that, they have, this is the carrier of concentration. It's 10 to the 22, so it's larger than ITO, which is the best, which is the semiconductor with the highest number of carriers. They have a large conductivity, mobility, and resistance. This is their crystal structure, so they are really well suited for being a transparent metal. This is the next, yes. So how can we make, from the theoretical point of view, how can we make a metal transparent? Well, we need correlations. So the simplest and the first way of attacking the problem, we considered Landau's Fermi liquid theory, where all these quantities are written in terms of the Landau parameters. So you have here the renormalized specific heat, written in terms of the bare one, and here we see the ratio of the masses. We have the susceptibility and the compressibility. And here I just presented to you all the bare quantities in terms of the electronic density of states at the Fermi level. So this is the basics of Landau Fermi liquid theory. But we need to calculate these coefficients. Here you see F0A, F0S. A is for antisymmetric, S is for symmetric. Of course, spin-related quantities should involve the antisymmetric Landau coefficients. For other non-magnetic or non-spin related, you have this S is for symmetric, not for spin. So in order to calculate these quantities, one can do, for example, is to start from the Hubbard model, which is the simplest model to introduce correlations. And if you start with the Hubbard model, you can do, for example, you can search for a Gutzwiller wave function to describe your ground state. And if you do the calculations in the approach by Gutzwiller, you obtain these quantities here. So what are the main objects here? I have U and UC. Well, U is my Hubbard interaction. This is the parameter I'm going to control. U equals 0. U equals 0. I am here at the free electrons. U equals to UC. This C is the critical value of U for the Mott-insulator transition. I don't want to be either in either of the two extremes. I want to be here because this is the guy. This is the strontium vanadate. But now I have this Landau parameters, all of them related to U. So I will be, I'm making sure that I am between 0 and UC, and the results we're going to present are valid only inside this window. So you can, well, this is the definition of the density of states, but the important ingredient is here. How the effective mass renormalizes. It renormalizes in terms of the Landau parameter F1S, and it's simply 1 divided by 1 minus the ratio to the second power. Now we plug this into the expression for the plasmon frequency, and we obtain here this expression. Remember that the coefficient is simply the plasmon frequency at 0 correlation, so we get some curve that decreases from 1. The ratio between the correlated plasmon frequencies to the free plasmon frequency, it decreases from 1 to 0 at the Mott-insulator transition. We want to be away from this Mott-insulation transition. No, this is done at 0 temperature. So the results for the Landau parameters, the Gutzwiller, there's also the Brinkman and Rice paper where they show that it's general for different filling. There is one modification. If you put a huge bracket here, there is a numerical constant that away from half filling, it's 1.08, something very close to 1. So we are considering that this constant here is just 1, and we are moving forward. This is Gutzwiller. This is you write down a wave function and you do a variational approach. No, no. And they even get the Mott transition, the Mott insulated transition. But I'm not going to go beyond U critical. So this is the curve for the plasmon frequency as a function of the correlations. And you see that it decreases. So imagine that I want to place inside this correlated metal, I want to place an emitter that has a characteristic frequency that I've chosen randomly. For example, here 40% of the value of the bare plasmon frequency. So it's clear that if I increase the correlations enough, if I don't increase the correlations enough, I will be in the reflecting region, and I will put the emitter and I won't see anything. But if I keep increasing correlations, then I arrive at a regime where the plasmon frequency is smaller than the emitter frequency, and I can have a transmission. So I have hope of seeing something. I put an emitter inside the material, and I see when it emits light. This is controlled by interaction. So this is another way of looking of what I've just said. The blue line, you have the bare plasmon frequency. The red line, you have the renormalized or strongly correlated plasmon frequency. And for an emitter that is here in between, you can control U, making the red curve goes to the blue and go to the back again. And then you can have a transparent and reflecting versions of the material. Well, this is not the story, the whole story. Now my atom is inside a medium. So I have to look at what happens to the atomic polarizability inside the medium. Fortunately, the spontaneous emission rate can be written in terms of the linear static polarizability of the atom in this fashion. And now I have a dipole with a typical oscillation frequency, and I have a metal with a typical plasmon frequency. It's intuitive to imagine that if these two frequencies are close together, you should have some resonance or some amplification effect. This is indeed what happens if we calculate the renormalization of the polarizability due to the presence of an electron gas, and this is just the electric susceptibility of the electron gas. What we get is, in terms of the static bare polarizability, we can rewrite things, and we end up, this is the final result. So the spontaneous emission rate, we already saw that it's the vacuum case multiplied by the index of refraction, but now I have also a correction due to the polarizability. It's a resonance of the oscillating atom with the oscillating electron gas. And this is the plot that I wanted to show you. So the Purcell factor, what's defined by the Purcell factor, is the ratio between the spontaneous emission rate not in the vacuum to the value in vacuum. So I would get 1 here if I were in the vacuum all the time. The blue line is without the polarizability correction, so simply the gamma 0 times the index of refraction. And as we know, the index of refraction goes to 0 at the plasmon frequency. So we have always in the medium, we would only have the decrease of the spontaneous emission rate and 0 to the left here. So it depends on where you place the emitter energy. If you place the emitter energy to the left of number 1 here, it's reflective, doesn't transmit, and you don't have a spontaneous emission. If you place it to the right, if it were not for the renormalization of the polarizability, we would have a very small, here is the blue line, very close to 1. We would have a very small spontaneous emission rate, but because of this resonance, you can have a very high emission rate. It still is lower than the vacuum, but this can be considered a Purcell effect, because why? Because the red line is above the blue line. So it's a Purcell effect inside the medium. So our idea is the following. Yeah, we have a way of switching on and off the emitter. So for that, all you need is a transparent metal, and this you can get by varying the interaction. For example, the strontium vanadates and the calcium vanadates. And you need an emitter with a characteristic frequency close to the plasmon frequency. And if you make this, well, I couldn't make the continued oscillation here. I was trying until 2 a.m. in the morning, but this guy here was, so this is what we expect to obtain once you vary U for an emitter that has a characteristic frequency close to the plasmon frequency. This can be done, by the way, by applying pressure, because we know that the correlations, they are sensitive to pressure through the compressibility. So if the idea is if you squeeze one of these materials, it goes from reflecting to transparent and blinking. So it would be a blinking device. So I conclude by reminding you that the main object of our work is the plasmon frequency. Metals, they typically have very large plasmon frequencies, and that's why they have good reflecting properties, and they do not transmit. Semiconductors, on the other hand, they have low plasmon frequencies, but they are not very good conductors. And for the community of the photovoltaics and displays and solid-state lighting, what would be nice would be to have transparent material with very good conducting properties. And this can be done by making metals transparent in the visible for a large enough Hubbard interaction. This can be done, of course, this can be easily done in the optical lattice, where you can control the U explicitly just by switching a button. But in order to make real devices, display devices, you need a solid-state system. And for this goal, I think that strontium vanadate and calcium vanadate are good candidates. The spontaneous emission rate here, it is suppressed at the plasmon frequency because you multiply the vacuum value by the index of refraction, but you can get, this is similar to what people do in photonic lattices. You can engineer photonic lattices to make a sharp resonance close to the gap, and then you can make the same, you can have the same type of physics. But here we are doing this in a solid-state material. It's not on a photonic lattice. And I'm from solid state, I'm from condensed matter. I like to think that I can make a material, I can cook up a material, inject some emitters, and then to make a display where I can have enhanced spontaneous emission. And then I finish here with these conclusions. Thank you very much. Edu.